So welcome, hi everyone, and welcome to this morning session. In this session, we will have three speakers. Each speaker has 35 minutes for the presentation, followed by 10 minutes of discussion. And the first speaker is Masahide Yamaguchi from Tokyo Institute of Technology, and he will tell us about polychronic tunneling. So Masahide, the stage is yours.
Thank you very much for your introduction. And I would like to thank organizer, especially Koshire Suraban, many people, and for giving me a chance to give a talk here and organizing this wonderful workshop. And sorry, until yesterday, I went to the ski resort and could not join this meeting. Sorry, yes. And today I'm going to talk about polychronic tunneling. And actually, we are going to propose some new tunneling process. So and this work is based on the two young postdocs, Naritaka Oshita and Yutaro Shoji. These young people worked very hard. And the contents of my talk is as follows. First of all, I would like to give some brief introduction on the conventional approach to quantum tunneling, especially quantum field theory. And here, in order to solve some problem in such approach, we take a different formalism to the quantum tunneling, so-called Polyadult approach. And maybe many of you are familiar with, but I'm going to briefly explain what the Polyadult equation and the WKB ansatz. And finally, we are going to propose some new tunneling process we call the polychronic tunneling. And in that part, I'm going to explain the methodology and very surprising result. And finally, I summarize my talk. So let me begin with some standard approach of the quantum tunneling. This is the potential of the one-dimensional point particle system with the following typical tunneling potential. And of course, equation motion is given by the this Newton equations. For simplicity, we take mass equal to B unity. And as long as a particular energy or energy scale E is smaller than the some potential height, then we don't have no classical dynamics from the transition for the transition from x1 to x2. And especially a particle sitting on x1 stays there forever classically, but of course, as you know, quantum mechanically, it can decay into x2. And when we try to estimate this tunneling approach, basically we have only to solve the Schrödinger equation like this one. And in order to get wave functions, we take this exponential form of the, we derive the wave function in terms of S. And just inserting this form of the wave function, we get the equation motion for S. Okay. And as is often done, we make a WKB approximation, or in terms of H bar expansion. So order by order, if we insert this expansion into this original Schrödinger equations, leading order, we get this one. This is nothing but the Hamiltonian-Jacobi equations. And the next leading order, we get some equation for x1s. And of course, if E minus Vs is smaller than 0, S naught must be imaginary, which again implies that no classical dynamics. But here, we have only to estimate the Schrödinger equation, or we have only to estimate the wave function. So even S naught is imaginary, no problem. And finally, we get S naught like this one, and S1 is something like that. And by making some matching conditions, we finally get a wave function and can easily estimate a transition rate, which is given by this famous formula. Okay, this is a standard approach of the quantum mechanics, quantum tunneling in quantum mechanics. And we can de-interrupt this transition rate in another way, so-called path integral approach. Okay. Again, we get with the same potential, which is a typical potential for quantum tunnelings, equation motion is given by this one. And again, in this case, no classical dynamics. But if we make weak rotations, tau equal IT by introducing the imaginary time, apparently, this equation motion has a classical dynamics, even for this case. Okay. And this exponent of the transition rate can be reinterpreted as a action for this classical dynamics with imaginary time. Okay. So basically, we have only to estimate the Euclidean action for so-called bouncing solution, which start from x1 and reaching x2 and going back to x1. Okay. So by finding this bouncing solution and evaluating its Euclidean action, we can estimate this exponent of the transition rate. Okay. And this can be also easily understood just if we make a path integral approach to the transition rate. This is nothing but the saddle point for the imaginary time approach. Okay. So in quantum mechanics, this Schrödinger approach, wave function approach and the WKB approximation is completely same with the path integral approach and the reading of the saddle point. Okay. These are completely equivalent. And now we go back, we are going to the, doesn't work. We try to generalize this result to the many body systems, or QI. Okay. And basically, through this idea of this transition rate or Euclidean path integral approach, we have only to estimate the Euclidean action for a path with the least Euclidean actions. Okay. Because, for example, in case of the many body systems, we have many paths which are starting from the metastable state to the true vacuum state. But least Euclidean path, path with the least Euclidean action is dominant because transition rate is proportional to the exponential minus SE. So as SE is smaller, transition rate gets larger and larger. Okay. And we can make the further generalization to the quantum field theory with just to this many body system to the infinitely many body systems in some sense in the quantum field theory. So we have only to estimate the Euclidean action, okay, and try to find bound solutions. And once we get such a bound solution, we have only to estimate the Euclidean action, which gives the transition rate by inserting these formulas. Okay, but please notice that there is a crucial difference between the quantum mechanics and the quantum field theory. You see, in quantum field theory, we have a gradient energy. Okay. Then, even in the quantum field theory, we have only to make a very completely same approach based on this Euclidean actions. We get classical dynamics, and Coleman et al. Prove that a solution with the highest symmetry, in this case, O4 symmetry, gives the least Euclidean action. So we have only to solve this equation with this O4 symmetric assumption, which rho is just a radius of the this spherical symmetric radius, you see. And with the boundary condition, rho equal infinity, field should go into the local minimum. And this from the regularity of this equation, d phi d rho at rho equals 0 must vanish. Okay. So once we get this bound solution, we have only to plug this bound solution into this action. Then we finally get this exponential. And if you wish to this prefactor, you have only to go beyond the one loop potential, one loop expansion, and finally we get display factors. Okay. And here, we have only to consider the field theory in the Minkowski or Euclidean background. But once we try to take into account gravity, you see, we have to include the action. We have also included the Einstein-Hilbert action into the action, because this is the Euclidean Einstein-Hilbert actions. And again, we have only to solve the Euclidean equation, but not only the scalar equation motion, but also the Euclideanized Einstein equation motions. Okay. And different from the case without gravity, no one has yet proved that highest symmetric solution gives the least Euclidean actions. So in all of the papers considered so far, just we simply assume that O4 symmetry gives the most probable actions. Okay? And once we make such assumptions, we have only to solve this scalar equation motion and the Friedman equations. Okay? And the crucial difference between the case without gravity and with gravity, you see, in the case without gravity, this law parameter Cauchy, you see, can run from 0 to infinity or, you see, unbounded. But for example, here, if we consider the Euclidean version of the de Sitter space, which is nothing but spheres, so ranging of the Cauchy is limited, different from the case without gravity. You see, then we cannot have a bouncing solution from this part to this part, you see, connecting to psi f, you see. Without the case, in the case without gravity, we can go into the phi f. But with gravity, Cauchy can take only finite range, so we cannot not necessarily go into the phi pi, you see. So with gravity, turning start from the higher energy state. And this can be easily understood physically. This is just coming from the quantum fluctuation of the de Sitter spacetime. Okay. And anyway, you see, Coleman et al. Proves that solution with the highest symmetry gives the least Euclidean action, which is sometimes equivalent to the most probable process when gravity is not taken into account. Okay. But if we take into account the gravity, no one proves that the solution with the highest symmetry gives the least Euclidean action, and which is not necessarily the most probable process. Actually, Euclidean action is never bounded from below or nor even from above, you see. So this is a still open question, you see. Not almost, all of the papers previous given so far is just simply assume that, you see, solution with highest symmetry gives the most probable process. Okay. And in this talk, I would like to try to address this question. And our approach is to use the Polyadult formalism, different from rather than the Euclidean path integral approach from the beginning. Okay. And as you might know, you see, I'm briefly introduce the Polyadult formalism. So let's consider the gravity and the matter system. In this case, matter consists of the scalar field. So we are interested in the evolution of the foliated spacetime and the scalar. Okay. And just 3+1, based on the 3+1 decompositions, Hij is just a metric on the some 3 surface. So what we would like to try to estimate is the wave function for the state before tunneling and a state after tunneling. Okay. And like in the quantum mechanics, we have only to take the ratio of the two wave functions for these two states. Okay. This is what we would like to do. And just we have only to 3+1 decomposition to formulate the Polyadult equations. Now this is the action. You see, Einstein-Hilbert action plus some scalar field with canonical kinetic term and the potential. And as is well known, just we have only to make a 3+1 decomposition for metrics by introducing a lapse and shift and 3 metrics. Then we have four first-class constraints. Two of them are primary constraints. Lapse and shift doesn't have a corresponding free independent canonical momentum. And the secondary constraint gives a so-called Hamiltonian constraint, momentum constraint. You see? And if we try to quantize these systems, there are many ways, but one way is first try to quantize alien variables. Okay, and we have a constraint, so restricts the wave functional space they operate on to solve the constraint. So now we try to quantize alien variable Hij, phi, n, ny, like this one. And by taking into account these constraints, we try to restrict the space, you see. Then these two first constraints, pi n and pi ny, just implies that wave function of psi shouldn't depend on n and ny. Okay. So this is just a super space. And Hamiltonian constraints just give the so-called Polyadult equations. And we have only also solved the momentum constraint. Okay. So this is a famous Polyadult equations. Capital phi represents phi scalar dynamics and Hij simultaneous. Hij is just a 3 metric. Okay. And just some metric gamma mn is introduced like this one. Okay. And as you know, Polyadult equation is a very good, has a very good features, some local equation, but it is often said that no time is given, you see, due to the Hamiltonian constraint. And this case, kinetic term is not necessarily positive definite, and the potential term is not necessarily positive definite. And actually, yeah, I don't go into the detail because people are familiar with this topic. So in fact, due to the constraint, especially the Hamiltonian constraint, apparently this system has no time. Okay. But as is already pointed out by the original paper given by Deutsch, external parameterization is relevant in this case. Rather, internal parameterization based on the geometry, like a cosmic expansion of matter in the universe, is relevant for the dynamics or evolution of the system. Okay. So we actually, what we would like to do, or we would like to have, is, you see, evolution of the 3 metric and phi before tunneling and after tunneling. You see, so by using the external time, we have only to introduce some new parameterization or parameter, which connect the state before tunneling and to a state after tunneling. You see. So we introduce a new parameter. Yes. As I told you before, from SI correspond to the some state before tunneling of the configuration. Capital phi is a scalar configuration phi and a 3 metric Hij. And SF is some configuration for phi and Hij after tunneling. You see? So we don't consider the some 4-dimensional manifold. Rather, we take just special path. You see, arrange some path parameterized by S. And such a path it represents an evolution of phi and Hij. Okay. This is what we would like to do by using the Polyadult equations. Okay. And As is the same with the case of the quantum mechanics, we expand the wave functional in terms of the h bar, you see, by use. This is just a WKB ansatz. And the leading order term gives the so-called Einstein-Hamilton-Jacobi equations, which is gives some evolution of the wave function of the theta, or strictly speaking, the exponent of the wave function. And what we would like to evaluate is this evolution of this theta 0 from SI to SF, you see, before tunneling and after tunneling. Okay. But we cannot take a arbitrary path because this is a Hamilton-Jacobi equation, you see, Einstein-Hamilton-Jacobi equation, which enable us to estimate the evolution of this theta naught. Theta naught is the exponent of the wave function. Okay, we would like to estimate the evolution of this theta naught. And the WKB equation or Einstein-Hamilton-Jacobi equation just gives the directional derivative of this theta naught, not a generic derivative. Okay, so unless this direction does not coincide with the direction of the path we give, you see, if they are different, this Einstein-Hamilton-Jacobi equation does not give the enough information to follow the change of this theta naught, you see. So only when this direction or directional derivative, you see, coincide with the direction of the path, this equation enables us to follow the wave function along the given path, you see. So we make this assumption, or we should say, we take such a path. And so once we impose this direction is proportional to Vn, what we have to do is just to fix the proportional coefficient. Okay. So to fix the proportional coefficient, we have only to insert this relationship to the this original Einstein-Hamilton-Jacobi equations. Okay. So once we insert this relation, this is the proportional, including a proportional coefficient, we can parameterize the phase change through the this simple formulas. Okay. So this is a phase change along this path before tunneling to the after tunneling. Okay. So we have only to estimate these quantities to estimate the phase change. Okay. And finally, to fix this proportional coefficient, we have only to insert the Einstein-Hamilton-Jacobi equation, or just a Polyadult equation in the leading order. We get these equations. And we can, if we identify this proportional coefficient to be lapse, okay, and S, which is a parameterization, parameterizing the path to be identified with some time coordinate, this equation can successfully reproduce the zero-zero component of the Einstein equation of Hamiltonian constraint. Okay, so apparently S behave like time, but please notice that we never arrange the 4D manifold from the beginning. S is just a path, you see, for the evolution of the phi and 3D metric Hij. And then S behave like a time, but it can take either Lawrencium and Euclidean time. Okay. We don't arrange the Lawrencium time from beginning, or even Euclidean time from beginning, just to take the parameterize the path through S. Okay. And at the leading order, if we identify alpha to be lapse and S to be identified time, if S behave like a Lawrencium, it's nothing but this Einstein-Hamilton-Jacobi equation, or Polyadult equation completely reproduce the Einstein equation because this is in some sense saddle point or leading order terms. Okay. And what we would like to estimate is not only this exponential factor, but to be honest, we'd like to, if possible, we'd like to estimate the rate. But in our formalism, you see, we cannot define the time properly. You see, in order to define the rate, we have to define the time. You see, rate is how many times tunneling happens per time. But in our formalism, we cannot define the time. So we can estimate only the this exponent. Okay. But this situation is the same with even the standard approach of the tunneling rate in terms of the Euclidean path integral formalism with gravity. You see, this prefactor is given by the loop, one loop factor or Gaussian integration. And once we take into account gravity, we cannot normalize such prefactor. So we just estimate this exponent of the tunneling rate. So in this sense, our formalism is as bad as Euclidean path formalism. You see. But this prefactor also gives a very important information. So now with our formalism, we would like to address the following question. Is the nucleation of the Coleman-Lucia bubble, which is based on the Euclidean path formalism and the highest symmetric bound solution, is the most probable or not? Okay. So in this approach, we have only to estimate this evolution of this theta because this is nothing but the exponent of the wave function. You see. So to estimate the tunneling rate, we have only to estimate this exponent, okay, and take an imaginary part of this exponent to estimate this b, okay. Now let's consider this problem with our formulations, okay. So in what we have to do, what we did is just this one, you see. As I told you before, we parameterize the path through this S from 0 to 1. And 0 is some false vacuum state, transition start. And S equal 1 corresponds to the state after transitions, okay? And in case of the Coleman-Lucia tunneling bound solutions, you see, S equals 0 simply corresponds to the just a false vacuum state. And as S becomes larger and larger, tunneling happens, and at S equals unity, tunneling completed. And in the Coleman-Lucia case, you see, or Euclidean path formalism, alpha square always negative, which implies that lapse square is kind of negative, you see. So this is just it implies that the time is Euclidean. Okay. And what we try to find is that make a randomly perturb this configuration and optimize the configuration to find a solution such that we try to find a stationary point, or I should say saddle point, and try to find whether there are the more probable decay process than the CDL configuration or not. And of course, in principle, we don't need to assume any symmetry, completely generic configurations, but it's too much complicated. So we still impose O3 symmetries, but which is less symmetric than the O4 symmetry, like CDL solutions. Then this is a result of our solution. You see, this B is an exponent of the tunneling rate. So expansion tunneling rate is proportional to exponential minus B. So as B is smaller, rate gets larger and larger. And surprisingly, we found some solution which gives more probable tunneling rate than Coleman-Lucia solutions, you see. And this is really gets some saddle points. See? And different, again, this is the field configuration of the Coleman-Lucia case. You see, S equals 0 corresponds to the forced vacuum decay. And as the S gets larger and larger, configuration becomes just a, you see, bouncing solution. And around these regions, phi reach the true vacuums, you see. And what we found the new solution is that this solution accommodates not only Euclidean path, but also Lawrencian path simultaneously. You see, in the dotted region correspond to the Lawrencian path, and solid configuration represent a Euclidean evolution of the configurations. Okay. If we allow such a configuration for the tunneling process, it can give the more probable solution process than the CDL process. And now let's take these evolutions in the more closer details. You see, first of all,
you have 5 minutes left.
Yes, I'm going to finalize my talk. Okay, this dotted line is correspond to the top of the potential. You see, so below this one, around this region, this is the left side of the potential barrier, and this region, large phi, correspond to the field configuration, right-hand side of the potential barrier. Okay, so before potential barriers, Euclidean region proceeds, you see, evolves faster, and the Lawrencian region are dragged, you see. So tunneling process happen for Euclidean region first, then Lawrencian region can overcome the potential barrier thanks to gradient energy, you see. Because if we have a field is inhomogeneous, thanks to the gradient energy in the field case, a potential field try to get homogenized. So once Euclidean region try to overcome the potential barriers, you see, Lawrencian region is dragged due to the gradient energy. And after potential barriers, okay, oppositely, Lawrencian region proceeds because just in the Lawrencian process, once the field overcomes the potential barriers, you see, just such fields rolls down along the potentials. So Lawrencian regions proceed, and then Euclidean regions follows, thanks to the potential gradient energy or by dragging of the Lawrencian region. Okay. And how to interpret this polychronic tunnelings? Okay. Key point is gradient energy in the quantum field theory or dragging. As I told you before, you see, only Lawrencian regions contribute to the tunneling rate. And as we observed, you see, before potential barrier or Euclidean region proceed through the tunneling process. So first, as a Euclidean process, tunneling happens, you see. But once such regions tunnel through, thanks to the gradient energy or by dragging, these remaining parts overcome the potential barrier as a Lawrencian process due to the dragging. Okay. This is what we found. So let me summarize my talk. Okay. Before summarize, but still there are many open questions, you see. In order to make a more detailed analysis of this new process, of course, analytic method or analytical analysis is indispensable. And we found that some process gives a more probable rate than the CDL, but we have not yet found the most probable process and how to characterize it. Okay. And if this Dirac or gradient energy is important, you see, in our case, more or less sick-wall case. So does this happen even in the syn-wall? And does it expand after the nucleation? And what if gravity is turned off? And as far as we make a simulation, as less after the coupling to gravity gets very, very small, kappa gets smaller, still we found a more probable process than CDL. But we have not yet completely confirmed. And can we formulate a thermal transition like a Hawking muscle or something? So finally, I summarize my talk. We have formulated a quantum tunneling in the process of gravity using the Polyadult equation rather than standard approach of the Euclidean path integral formula. Okay, and our formula accommodates the coexistence of the Euclidean and the Lawrencian evolution because we didn't arrange the four-dimensional manifold. You see, we are interested in just a 3D evolution of the 3D metric and scalar field phi, and characterize some path. You see, parameterized by S. Okay. We consider such formulations, and S can be mimic the Euclidean time or Lawrencian, both. And we confirm the consistency of the CDL result, which is most exclusively described by the Euclidean path formalism. And the new formulation allows us to consider the new tunneling process. We name the polychronic tunneling that has a much higher tunneling rate than the CDL. And that accommodates not only Euclidean formalism, but also Lawrencian evolution simultaneously. And such process exists even in the decoupling regime of the gravity. Okay, thank you very much.
Thanks, Masahide. Okay, so I see already a question by Alberto.
Thank you. Can you hear me?
Yes.
Hello.
So, hello. I have a question about the Wheeler-DeWitt approach, let's say, to this problem, and a general question. So, as far as I understand, you assume Einstein gravity in this talk.
Yes.
Okay.
Yes.
So the question is, how do you modify the Wheeler-DeWitt equation in case you have a modified gravity? You have other terms in the action apart from the Einstein-Hilbert term.
In that case, basically, as long as the original action has a 4D diffeo, I mean that just a diffeomorphism invariance.
Yeah.
And as long as it's a first class constraint, I mean the Hamiltonian constraint and the momentum constraint are first class. Equation motion, I mean the apparent equation motion would be modified. But basically, I think the approach itself is the same. Just a Polyadult equation is modified. Okay. I mean just for example, just an expression of this Hamiltonian is modified. This expression would be modified according to if you introduce some modified gravity term.
And is it known how to modify it? If you know
it depends on what kind of extension of the Einstein gravity. For example, if you introduce non-minimal couplings, I think some I don't have a concrete form, but it's not so difficult, I think. But in case of Horndesky, if you consider, maybe I'm not sure it is already well known or not.
I see. I also have another question.
Yes.
So it is known that Einstein gravity is not UV complete because it's not renormalizable. So you have to be careful with this and stick to energies that are sub-Planckian in some sense. So how do you check that your results are within the range of validity of Einstein gravity?
Okay, very nice question. Yeah, so this is exactly in some sense, we don't go into the prefactor or even not a sub-leading order, you see. In some sense, we just take a tree-level approach. It's just a classical dynamics and the leading order of the WKB. So if we try to make, you see, if we really try to estimate this tunneling rate, including the prefactor, we have to, in some sense, renormalize, or we have to make a UV complete of the gravity theory. But it's too much for us, at least at present. So we don't go into such a difficult problem. In some sense, we just estimate this exponent of the transition rate, and this is something like how to say, tree-level approximation.
But still, I mean, if you use the Coleman-Delucci approach to do that, you have to be careful. You have to make sure that the curvature is small in Planck units. Otherwise, you go outside the range of validity of Einstein gravity.
Okay. So
how can you check the equivalent thing in your approach with the Wheeler-DeWitt equation? This is the question.
Oh, so in this sense, I think as long as this Euclidean action or even our action is larger than h bar, in some sense, semi-classical approach is more or less justified.
So I have to look at what action? Sorry.
This Euclidean action, SE. This SE is much larger than h bar. Semi-classical approach is more or less justified.
Oh, okay.
And
so
in this
also,
sense,
So you're saying
in this sense,
you're saying that also in the Wheeler-DeWitt approach, at the end you get an Euclidean action.
Well, we can estimate such a, how to say, not necessarily, our case is not necessarily Euclidean action. We, in some sense, this wave function includes both Euclidean part, I mean the real part and the imaginary part. You see, this S node. And so, strictly speaking, in our case, as long as this theta node is much larger than h bar, this WKB answer is more or less justified, and the semi-classical approach is justified.
So I have
in
to
this sense, in this sense, it's checked,
Okay, so and did you check it for your result?
Yes, in this sense, we have checked it.
Okay.
And in the standard case, this is just a Euclidean action. It's not exactly coincides the Euclidean actions. And CDL case, as long as Euclidean action is much larger than h bar, it's okay. You see, at least semi-classical approach within the region of semi-classical.
I would quickly now give the word to Lucas Moldon, who has another question. Okay.
Okay, can you hear me?
Yes. Hello.
Hi, Masahide. Very nice talk. I have curiosity. Where do you think you can observe such tunneling? Which kind of experiments? This high-rate tunneling.
So I didn't mention the concrete example, but of course, you see, quantum tunneling was paid particular attention to some inflation and some landscape, you see, in old days. But recently, I try to apply our method to Higgs instability. For example, as you know, you see, lining of the coupling might be negative. So this result might suggest that our current vacuum is not completely stable. It might unstable into the deeper vacuum.
I see.
And as far as I understand, in the current precise calculations, our vacuum is metastable, safely metastable. I mean that it's still metastable, but its lifetime or inverse of the tunneling rate is much higher than the cosmic age. But I'm wondering if we take into account our new process, our vacuum is really safe or not, which might give the constraint of the, for example, top quark mass.
I see.
Yeah,
So
this might be the
accelerator experiment.
Yeah, this might be the concrete application.
I see. Very interesting.
Okay.
Yeah.
Let me quickly comment on that, because I think that such a calculation has been done also in the presence of gravity a couple of years ago, like in 2019 by Branchina, Dario Zappalà, and Eloisa Bentiveglia. But they started from, they used the Coleman-Delucci approach, and they started from a no-4 symmetric solution. So it is possible that in your case there would be corrections, but you might want to have a look at those works.
Thank you very much. Yeah.
So I see that there is a question by Shravan, but Shravan, would you mind if we postpone it to the discussion session, because we are a little late?
Yeah, sure. No problem.
Okay, great. So let's thank again Masahide.
Thank you very much.
Okay, and now the next speaker is Carlos Herdeiro.
Hello.
Are you there?
Good morning, everyone.
Can you start sharing your screen?
Hello, Carlos. You can share screen. I made you co-host.
Okay. So can you see my screen now?
Yes.
And my slide?
Yes. And yeah. Can you
Okay,
move
perfect.
just to see if it looks.
I can see. Hello, Carlos. How are you? Paulo Muniz aqui.
Hello, Paulo.
Oh, I can see the slides. Thank you for being here.
Thank you. Thank you for organizing this. So you can see, everyone can see my slides?
Yes.
Yeah, sure.
Perfect.
Second is Carlos Herdeiro from Herdeiro University, Portugal, and he will talk about the Hamiltonian game bosonic stars, ultralight dark matter, and the gravitational waves. Please, Carlos, you can start.
Okay, thank you so much. Thank you for having me. Good morning, everyone. Let me start by saying it's really a pleasure to give this seminar, this workshop. Thank all the organizers, in particular, Alexei, Paulo, everyone in the organizing team for the kind invitation. So my title reads The Imitation Game, Bosonic Stars, Ultralight Dark Matter and Gravitational Waves. And my goal is to discuss with a very concrete example and real data how strong gravity systems and observables could assess the nature of dark matter, or at least part of it. In other words, I shall entertain the possibility, if and under which circumstances, current strong gravity observations, which recently have undergone some remarkable breakthroughs, in particular with gravitational waves, could work as the new particle detectors. So let me apologize and ask the permission of the chair by saying that my talk should last a bit over 35 minutes, maybe 40, but I'll leave some time for discussion. Okay, so let me start.
Let's time for questions.
Okay, thank you. So the questions I will address become particularly interesting in the context of some so-called fuzzy dark matter models. So let me set the stage with a few preliminary remarks here. Before a decade or so ago, fuzzy dark matter referred essentially to particles in a mass range around 10 to the minus 21 to 10 to the minus 23 electron volts. And these were designed to explain galactic halos. These are still being explored by cosmologists, having in mind that the original evidence for dark matter are galactic rotation curves, which suggest the existence of such dark matter halos. And here's a typical galactic rotation curve, and one needs a dark matter halo to explain it, since the visible matter in gas and disk are not enough, assuming standard gravity. But in the last decade, greatly motivated by the possibility that there is a landscape of such ultralight particles, well, from string theory compactifications, a scenario called the string axiverse, models of such hypothetical ultralight bosonic dark matter started to be explored in a wider mass range. And in particular, in the 10 to the minus 10 to 10 to the minus 20 electron volts mass range, strong gravity systems and observations could provide smoking guns of their existence or falsify such models, as I shall explain. So why strong gravity systems? Well, perhaps one should be asking at this point in the development of theoretical physics, where shall we be looking for the unknown in the near future? And of course, traditional collider particle physics, which has given us so many beautiful results and advanced so much our understanding of the fundamental constituents of nature, may be stalling, since the next energy frontier requires challenging financial investments and technological issues. And on the other hand, nature does provide wonderful extreme physics laboratories. And in strong gravity, there's a new era of unprecedented precision observations, which started in the past decade or so, precisely probing the nature of some of these extreme physics laboratories, such as black holes. Now, at the forefront of these observations are gravitational wave detections. So the gravitational wave era started back in 2015 with a chirp. And this is what you see in this slide, is the first detection, the celebrated GW150914, where, of course, this stands for the date of detection. And the plot shows what's called the strain, essentially the metric perturbation due to a transient gravitational wave versus time. And the strain is really a tiny number, which is at the source of the difficulty in making these measurements, whereas in this case, the time is a fraction of a second. The blue and orange lines describe the data from the two LIGO detectors that were the only gravitational wave detectors taking data at the time of this particular event. And the signal is a sort of sinusoidal curve with several oscillations, but increasing amplitude and frequency until a peak is attained, once the oscillations start to fade out and quickly do so. Now, instead of showing a strain versus time, one can also exhibit these events in a frequency versus time plot, like what you see here in these bluish panels. Now, the color code here denotes the power on each of the time and frequency beams. So events stand out from the background noise as a sort of track, distinctively seen in most of the panels, where both the frequency and the power are progressively increasing until some maximal frequency is attained. This typical shape is called the chirp. And whenever the signal morphology, this signal morphology is seen, it is interpreted as due to an in-spiral and merger of two black holes, or eventually neutron stars, depending on the masses involved, which were in a quasi-circular orbit, and with a final relaxation or ring down of the final black hole into equilibrium. Some events are longer, some events are shorter. In some cases, the power in the signal does not outstand so clearly from the noise, but the qualitative picture is roughly the same for all these events. Now, of course, these gravitational waves are a general consequence of systems of accelerated masses. And in a loose sense, they are the acoustic waves of space-time. However, due to the stiffness, if you want to think in these terms, of space-time, only dramatic events produce them with an amplitude that our technology may observe. So the main sources are binaries of compact objects, black holes or neutron stars. And at present, the LIGO-Virgo and also now CAGRA collaboration, LVK, released 3 gravitational wave transient catalogs from the first 3 science runs. So that's 1 plus O2, and this is O3A, and this is O3B, reporting a total of 85 candidate events and some lower significance triggers as well. So most events, albeit informative in many ways, they comply with the expected vanilla binary black hole models or neutron stars. Some, however, are challenging, and amongst these, GW190521 stands out, which I will talk about in the next slide, and of course we expect more data in the future with O4. So let me comment on this particular event, which I'll devote my talk to, GW190521. Now, the progenitors in this event were estimated when it was announced as the most massive of any event thus far, with about 85 and 66 solar masses. So this means that within the uncertainties, at least one is in the so-called pairing stability supernova gap. And this is a gap in the mass spectrum of black holes, of the black hole population, starting around 50 solar masses, wherein black holes cannot really form from the collapse of massive stars directly, according to standard stellar evolution. So the question is, how did the progenitors of this event come to be? Moreover, since this is a low-frequency gravitational wave signal, there is no in-spiral in the observed transient, so that would be below the LVK sensitivity band. And that leaves room to speculate about the true nature of the event. So by the way, GWTC3, the last catalog release, there's another event and some triggers which have a similar mass, and the analysis that I'll be reporting can also be done, and it's being done, but it's not complete. Now, the cutoff of the signal due to the low frequency that I've just mentioned is better seen in this plot. So the key aspect is that roughly the peak frequency of a signal scales inversely with the mass of the event. Thus, the heavier the objects involved are, the lower the frequency is seen up to the merger. So here in blue, orange, and green, we have the strain versus frequency of 3 events. In black, we have the power spectral density of the detector, which describes the noise of the detector and thus gives a threshold on its ability to measure a certain strain at a certain frequency. So observe, it rises at low frequencies because of the seismic noise of the Earth. This is called the seismic wall. And as one increases the mass of the event, which happens from blue to orange to green, only the very latest part of the transient can be seen by the detector. Thus, even if it is a binary merger, one may not see the in-spiral but only see the merger. So this is what happens for GW190521. Now, conversely, one may, of course, ask if there was really an in-spiral, and even if there was, if it was a circular one. So because of these various features, GW190521 is the first event to truly stimulate theoretical debate about non-standard interpretations. Now, in parallel, the issue of degeneracy has been a kind of an elephant in the room in gravitational wave detections. So the black hole interpretation seems vindicated within the Kerr black hole paradigm of general relativity. There is, however, an almost complete lack of alternative models for which waveforms have been accurately produced as to really assess the extent to which matched filtering, which is the technique used within a larger library of theoretical templates, really selects the general relativity black holes. And within this desert of alternatives, one oasis is provided by bosonic stars. Now, from the gravity perspective, they appear in general relativity, although they are generalizable to modified gravity as well, with simple and physically reasonable matter sources. These are complex massive scalar fields or vector fields, possibly with self-interactions, but certainly with a master. They can have a compactness comparable, albeit slightly lower than that of black holes, making them black hole mimickers that are dynamically robust. Moreover, they started to be evolved alone or in binaries, producing waveforms. And what you see here is the first orbital merger of 2 vector boson stars that we did a few years ago. The simulations are done with numerical relativity techniques using an infrastructure, which is the Einstein toolkit for this purpose. So they are certainly an excellent toy model, but there's been a lingering question if they could be something more. But one can also give them a more micro perspective. They are often described as Bose-Einstein condensates with many ultralight particles in the same quantum state, thus justifying the classical description. The need for ultralightness comes from the existence of a model-dependent maximal mass for the bosonic star. So this is the scaling. The maximal mass of the star goes as 10 to the minus 19 solar masses times the inverse of the particle's mass in GeV. Thus, for bosonic stars with mass in the astrophysical black hole range, so that they could mimic black holes, the fundamental bosonic particle must be ultralight with this range of interest here. Now, if such hypothetical particles have feeble or no interactions with standard model constituents, they are fuzzy dark matter, only detectable gravitationally. But what's their high energy physics origin? How can one have such light masses in a consistent model and protected from all sorts of corrections? Well, a possible origin is the so-called string axiverse that I've alluded to already, but there's also simpler extensions of the standard model where they could appear, and that's discussed in this recent paper here. Now, as working concrete examples, the discussion in this seminar will focus on these two classical effective field theories. But this is by no means exhaustive. So boson stars have been computed in many other models with self-interactions and more complicated couplings, and their dynamics is starting to be analyzed in a variety of models. But these two models stand out on a simplicity criteria. In both cases, we minimally couple a massive, complex bosonic field, a scalar in the first case, a vector in the second one, to Einstein's gravity. So in the second model, we have a Proca field. The corresponding solitonic solutions that we find in these models, and I shall describe, are called scalar boson stars or vector boson stars, also called Proca stars, respectively. Now, in both cases, the mass mu determines the maximal mass of the stars, as we discussed, and can be faced as a new scale. So bosonic stars can be lumps of dark matter and serve as black hole mimickers. Can they actually fit some of the recent strong gravity data, in particular gravitational wave observations? So such tentative possibility was raised in this paper here that was published last year in PRL. And here GW190521, so that mysterious event I mentioned earlier, was analyzed as a collision of spinning Proca stars. A likelihood Bayesian analysis using the same libraries as the LVK collaboration for black hole binaries, plus an extra library of waveforms of Proca star collisions, gave a slight statistical preference to the Proca model. Furthermore, this analysis could determine the mass of the ultralight vector boson, which came out to be 8.7 times 10 to the minus 13 electron volts. Of course, confirmation of the Proca star interpretation, for which more similar events are needed, would provide a very nice evidence, first evidence of a long-sought dark matter particle. And from O3b, there are a couple of other massive events, as I've mentioned earlier, that we are analyzing. And of course, O4 run and the following runs will certainly provide such events, making this type of analysis quite timely. But at the very least, this type of analysis serves to substantiate the degeneracy issue in waveform interpretation that we raised earlier. And this is what I'll be telling you much more about this event and this analysis in the talk. So enough for motivation, which was more or less what I've done so far, an overview. Let me now tell you a bit more about these bosonic stars, because I guess many of the people here will not be have worked on this, and the possibility that these LVK gravitational wave detectors become particle detectors in that sense. Now, these bosonic stars are self-gravitating solitons. It's perhaps worth recalling that in classical field theory, without gravity, there's a long history and a large literature on finding soliton-type solutions, which derive their name from solitary waves found within the Korteweg-de Vries equation, originally back in the 19th century. These are particle-like solutions in the sense of keeping their shape, as you see in this movie of a solitary wave propagating along a canal. Now, solitons occur for nonlinear field theories, and the constancy of their shape is interpreted as a cancellation between nonlinear and dispersive effects. There is, however, a generic argument known as Derrick's theorem against the existence of stable and time-independent solutions of finite energy in a wide class of nonlinear wave equations in 3 or higher spatial dimensions. But one way to circumvent the theorem is to consider a complex field with a harmonic time dependence, which guarantees a time-independent energy momentum tensor, like what you see here in this equation. Moreover, there's a global symmetry in this case and a conserved scalar charge, which is typically called Q. And then for some classes of potentials, which yield, of course, nonlinear models, localized stable solutions exist, which are known as Q balls, so balls of this charge Q. But in the presence of gravity, no scalar nonlinear interactions are required because effectively such nonlinearities are provided by the self-gravity of the field. So thus, if we take this harmonic time dependence, even for a linear scalar field theory, minimally coupled to gravity, one can obtain the solitonic solutions, which are precisely the scalar boson stars. And this is the simplest model, which is the same I've shown you before. Here are the field equations, where the scalar field equation is only apparently linear because it back reacts on the metric via the Einstein equations, and then the metric defines the D'Alembertian operator. So gravity gives the necessary nonlinearities. The action is invariant under a global U1 symmetry, which leads to a conserved current. And then integrating the temporal component of this fork current on a time-like slice leads to conserved charge, this Noether charge Q, and the Noether charge counts the number of scalar particles, essentially. Notice that this is a conserved charge in the sense of a local continuity equation, but there is no associated Gauss law, since it's a global rather than a gauge symmetry. Now, to get to solitonic solutions, which in this case are scalar boson stars, the simplest case is to assume spherical symmetry. Then the spherically symmetric solutions ansatz has three unknown functions, two from the metric sigma r and m r, and the latter from the latter is being called the mass function here, and one from the scalar profile phi of r. Note the harmonic time dependence we mentioned there, which introduces a frequency parameter. That's that small omega that will play an important role in the following. Now, one can think about the complex scalar field as two real scalars, both time periodic, but with opposite phases. And the time dependence cancels at the level of the energy momentum tensor, therefore being compatible with the stationary metric, or in this case, static. Then one plugs these ansatz into the Einstein-Klein-Gordon equations and gets from the Einstein equations two first-order radial ODEs for m and sigma, and from the Klein-Gordon equation, another second-order ODE. Now, to find the solutions, one must solve the three coupled nonlinear radial ODEs in the functions m, sigma, and phi, where the constant omega appears explicitly. Unfortunately, no closed form solutions can be obtained, at least in these astrophysical application setups. There's other more toy models where it's possible. So one resorts to numerical methods. And for instance, one can use a shooting method after finding the correct boundary behaviors for the three different functions near the origin and near infinity. I will not go into the details, but I'll leave here as a reference a set of notes and video recorded lectures by one of the PhD students in our group, Alexandre Pombo, addressing the numerical strategy and implementation to obtain such solutions. So once you do the numerics, you find a space of solutions. One way to represent it is in a mass. Here, capital M is the mass of the star, the ADM mass, versus frequency omega diagram. So it's this red line here. And for simplicity, we are using units such that mu, the boson mass, is absorbed in m and omega. Also, in this plot, the blue curve is that of the Noether charge. What you see here is that solutions only exist for a range of frequencies. For this model, the minimal frequency turns out to be 0.767 times mu, putting back the mu, whereas the maximal frequency is mu. The latter is a bound state condition, and it is rather model independent. For some frequencies, there's only one possible mass, one solution, whereas for other frequencies, there's more than one solution, several possible masses. And this defines a set of branches. Finally, you see there is a maximum mass for the stars, which if one puts the constants in is of the form that you see here, where this coefficient is determined by the numerics, the alpha ds, finding the space of solutions. This is the same formula that I've shown you before to justify the connection between bosonic stars and these ultralight bosons. The maximal mass solution actually separates the solutions that are dynamically stable from the unstable ones. This can be seen by studying linearized radial perturbations. So this is the maximal mass that you see here. And this is the stable branch to the right of it. And to the left, you have the unstable branch of solutions. Now, the dynamics of the unstable branch has been investigated, and depending on the solutions and on the perturbation, some solutions can migrate to the stable branch, some can collapse into a black hole, and some can disperse entirely in a kind of fission event. Using numerical relativity techniques, it's possible to evolve these stars as an initial value problem. This is just a single star to assess their dynamical robustness. And solving the fully nonlinear coupled Einstein-Klein-Gordon equations. And what I'm showing you here is one such evolution of a stable solution corresponding to a given frequency, in this case, 0.95. The two panels on the top show the real and imaginary part of the scalar field. And as the time evolves, what you can see is that they both oscillate and with an opposite phase. On the other hand, the bottom panel shows the modulus of phi squared, which, as we can see, it's time invariant, as it is the energy density. Thus, from the viewpoint of physical quantities, this is a static solution. This picture that I've just described for the spherical scalar boson stars repeats itself very closely, mutatis mutandis, for their vector cousins, that is for spherical Proca stars. On the left panel, you see the domain of existence of scalar boson stars, we've already described, whereas on the right panel, you see the Proca stars. Thus, we get a similar domain of existence. Again, the spiral type curve with a maximal mass, a minimal frequency. There's a maximal frequency. One can also show, studying perturbations, that the dynamical stability changes at the maximal mass, just as in the scalar case, with a stable branch to the right. I will also comment that the solutions I'm showing here are the so-called fundamental family of solutions for each case. There are also excited solutions for which the scalar or the appropriate component of the Proca field have more nodes. It's a bit like the orbitals in the hydrogen atom. So these are the ones I'm showing. The fundamental are typically dynamic. The excited ones are typically unstable, dynamically unstable, and the fundamental has a stable branch, typically. So here are the main points about the dynamical features of the spherical vector boson stars. First, there is a stable branch of solutions from the maximal frequency down to the frequency of the maximal mass. Second, there is a formation mechanism. I didn't go into detail, but there is a formation mechanism for the stars called gravitational cooling, also occurring in the scalar case. This means that starting with a dilute cloud of these ultralight bosons, they can gravitationally clump under their own weight, and they can form these compact stars. Finally, as I've already commented, one can evolve them in binaries, leading, if the two stars are sufficiently compact, the endpoint of this collision will be a black hole, and one can extract the corresponding waveforms of the process. So let me conclude this discussion on the spherical stars by referring you to this paper if you'd like to know more. There's a comparative analysis of the scalar and the vector case, and there's also some classical solutions of the Dirac-Einstein equations called Dirac stars. Of course, these latter ones are very different from a fundamental viewpoint, as one cannot have many such fermionic particles in the same quantum state due to Pauli's exclusion principle. Now, static spherical stars are, however, not the most realistic objects, because the real stars, planet, and most likely black holes, they rotate, they spin. One can indeed construct axisymmetric spinning stars as solutions of the models Einstein-Klein-Gordon and Einstein-Proca that I have presented before. This is done using these ansatz for the metric and scalar field. Now we have four functions of both the radial and angular coordinate from the metric, and a fifth function from the scalar profile. Also, besides the frequency omega, the scalar ansatz introduces an azimuthal harmonic index m, which is an integer. The Klein-Gordon plus Einstein equations now yield a system of 5 coupled PDEs, nonlinear. And to solve them again, one has to resort to numerical methods. One performs an expansion of the unknown functions, both near the origin and asymptotically. The equations can be solved using, say, a relaxation method, Newton-Raphson type. And for each frequency, omega, one can find various or no solutions corresponding to different star masses. The equations to be solved are much more complicated than in the spherical case. So here's the Klein-Gordon equation, and here are the 4 Einstein equations. Actually, this is a combination thereof that we choose to solve. So these are nonlinear coupled PDEs on 5 functions, depending also on these parameters, little m and omega introduced in the scalar field ansatz. So again, I will not enter the details of the method we use for solving these equations or the solver that we use, but I highly recommend these lectures by another of our PhD students in our group in Herdeiro, Jorge Delgado, and these were given at the school we organized some time ago in Herdeiro. And these are tutorials on how to obtain these solutions with a particular solver called FIDISOLV. There are many other methods, and other groups use other solvers. And these links include also a PDF and video recorded lectures that could be useful for anyone wishing to know more about these methods. Now, the upshot of the numerics is again to obtain a domain of existence of solutions, as in the spherical case. In a mass versus frequency diagram, fixing the azimuthal harmonic index little m equals 1, which is the fundamental set of spinning stars, one obtains a similar spiraling curve, as you can see here. Again, there is a maximal mass and the scaling is the same with mu, but the coefficient depends on this little m, although it is of order unity, at least for the lowest m's. It shows that the spinning stars with little m equals 1 can have a bit higher masses than the static ones that have little m equals 0. Increasing further m, there's a trend of increasing this maximal mass. There is a curious property of these spinning boson stars. The total angular momentum, capital J, is related to the total Noether charge, Q, by this simple relation. So fixing little m, the number of particles determines the total angular momentum. Now, the next interesting thing about these spinning boson stars is their morphology. They are toroidal in this scalar case. In a 3D plot, the surfaces of constant scalar energy density look like this that you see here. They have this toroidal morphology. And when we started studying the dynamics of rotating boson stars back in 2017, our first simulations revealed that they were dynamically robust. We were expecting also to have a branch of dynamically robust solutions, as in the spherical case. So analogously to what we did in that case, here's what you can see in a devolution of what seemed to be a stable spinning boson star. Again, the two upper panels show the real and imaginary part of the scalar field. And as time evolves, you can see they both oscillate and rotate, but with opposite phases. And on the other hand, the bottom panel shows the modulus of phi square, which, as we can see, is time invariant and toroidal as it is the energy density. However, as we pushed our simulations to be longer, we found in 2019 a surprising result. The most fundamental spinning scalar boson stars develop a non-axisymmetric instability at a moderately long time scale of the order of 1,000 light crossing times. So you can see it here in this visualization of a fully nonlinear evolution of the Einstein-Klein-Gordon system in the left panel. So here the color code denotes the scalar field amplitude. And so I'll put this again. When the non-axisymmetric instability kicks in, an apparent horizon forms. As you can see in the right panel, the mass associated to this apparent horizon is the blue solid line. And the energy associated with the scalar field is the green dashed line, which tends to vanish as it is swallowed by the black hole, signaling the formation of a black hole. So these stars collapse into a black hole. However, the instability is absent in the cousin-Proca model. At least this is what could be deduced from numerical evolutions with a timescale 10 times larger than the ones where the scalar instability was seen. Thus, spinning Proca stars are dynamically more robust in the simplest models. So in this paper that was published in 2019, we have suggested this difference in dynamical stability could be associated to the different morphology of these stars. The scalar stars are toroidal, whereas the vector stars are spheroidal. There is an analogy with models of rotating neutron stars, where toroidal solutions are possible, but suffer in general of a similar instability. However, let me comment that later work by ourselves and also by East and Simonsen suggests that the instability of the scalar stars can be cured by adding self-interactions, even in the scalar case. But within our working example of the simplest models, the conclusion remains that the Proca stars are dynamically more robust than the scalar ones. In fact, even if one starts with a spinning Proca star with a strong perturbation that visibly changes its energy distribution, as in this evolution that I'm showing here, no instability is seen within the time evolution, and the start approaches the equilibrium spinning solution, although oscillating in an asymptotic process, which is this gravitational cooling mechanism at work. And moreover, if one starts with an excited spinning Proca star, like this one here, that has an energy distribution which is Saturn-like, the evolution makes it decay to a spheroidal, fundamental spinning Proca star, again approaching an equilibrium solution. Okay, so given the dynamical robustness of spinning Proca stars, we have collided them in binaries. So the simplest such collisions are head-on collisions. Considering this over quasi-circular mergers has technical advantage. One may argue this is less astrophysical, which is likely true, but our point will be that even then, we can compete with the vanilla black hole binary mergers used for GW 190531. So here's the simplest setup, which can be generalized in several ways. Consider two equal mass, capital M, and equal frequency, omega, perturbatively stable, spinning, vector, bosonic stars. The spin axes are aligned, and they are perpendicular to the screen and pointing towards us. So they are initially at a coordinate distance d in the x-axis. They could both have a velocity vy in the opposite y-axis, but here we take this to be 0. This is what is called a head-on collision. Quasi-circular binaries would require a sufficiently large vy. Now, with this setup, we've performed fully nonlinear numerical relativity evolutions of the Einstein-Proca system. Here's a cartoon of the evolution. The bosonic stars have an eccentric trajectories. This is due to frame dragging. That is, they actually acquire the vy velocity because of the spin of the other star. And this is a well-known general relativistic effect. Then they merge and an apparent horizon forms. So the black hole is formed with a certain mass, mbh, and a certain non-zero total angular momentum, jbh. So in the simplest collisions, the two stars are equal. So in particular, they have the same frequency and the same mass. We can then extract the waveform of the collision process. Varying the stars we take as the initial data, this waveform varies. So here is a sample of the scanning of the parameter space. As we vary the initial stars, which we label by the frequency omega to be the ones indicated by the red arrow in the bottom panel, the waveforms of the collision process, as described before, also varies, as shown in the upper panel. Now, in this scanning, we do not go to too high frequencies. Otherwise, the final object is not a black hole and the signal is not compatible with GW190521. Let me also comment that these examples are for the stars in the binary being of equal masses, but we have also performed unequal mass collisions and we are continuing to do so at the moment. So to give you a sample, the initial analysis in this paper was done with about 100 waveforms and now we have more than 800. So finally, let me just emphasize, to make this clear, that the process to obtain these waveforms is a two-step process. First, one has to obtain the equilibrium solutions and then using them as initial data for the binary evolutions, extracting the waveforms. Now I can go back to the paper I've already advertised, where we found that the collision of two spinning Proca stars actually fits slightly better the data than the vanilla binary black hole model that was used by the LIGO-Virgo CAGRO collaboration. Firstly, let me show you in a bit more detail this event, GW190521. So the upper three panels show the strain data for the two LIGO detectors and the Virgo detector in light blue and in purple. So you see that was in light blue, in purple, and in orange, and in black. There are three different reconstructions of this signal. In particular, the orange contours are the models for circular mergers that were considered to be the most likely ones by the LVK collaboration. The most important thing here is that in this signal, unlike GW150914, the first detection that I showed you in the very beginning, one does not see a clear in-spiral track. One sees only a signal that grows and decays. One could imagine that instead of a binary, one could have a black hole that suddenly was perturbed for some reason, and then it rings down back to equilibrium. And in the bottom three panels, this is confirmed by the frequency map, where the typical chirp track that I've shown you before is far from clear. Now, in a bit more of detail, here's the signal, again in light blue. This is from the Livingston data. And in this plot, there's also the best fitting black hole model in green and black for head-on collisions and quasi-circular mergers, and Proca model, and that's for both the equal mass, Q equals 1, and non-equal mass, that's little q, which is the mass ratio parameter not equal to 1. You cannot see which fits better with the naked eye, really, but you can kind of see which one fits worse, and this is the head-on binary black hole, which is the green line, and if you look carefully, it fails to give enough power in the initial part of the signal, which is called the pre-merge. But a statistical preference requires a proper Bayesian analysis, which was done in our paper. This was led by Juan Calderón Bustillo, who also participated in the same analysis for LVK collaboration. And what we've looked at is this log base factor with different priors. And the conclusion is that the base factor is slightly or even considerably, but not dramatically, better for the Proca model. Also, the best fit is given by the Proca model. So the base factor, of course, is an integration of the likelihood of a given waveform over the space of parameters, masses, omegas, inclinations, some astrophysical considerations. And there's some weight given to these parameters, which is given by the prior chosen, the prior probability. So in the left model, what you see is the statistical preference, which is the difference between this log B factor. It's 80.9 minus 80.1, comparing the Proca stars with the binary black hole. That's a difference of 0.8. You exponentiate that, and it gives you a preference of about 2, which is not statistically significant. In the right, which is with a different prior, it's a bit better. So the difference there is 3.4, and the exponential of that is 30. So there's a stronger preference, but really strong preference typically requires about the difference of 5. So exponential of 5 is about 150 times preferred in this context. So the second column denotes the likelihood of the best fit, and that measures how a given waveform fits the signal. And this is the same for both priors, because the best fitting waveform does not depend on the prior. Now, then one may inquire within the Proca models, what is the probability distribution? So the statistical analysis gives a probability distribution for the frequencies of the Proca stars, which nicely fades out at the extremes of the range we've analyzed, which suggests we are in the right frequency range. Now, this gives a frequency distribution centered around 0.893, which determines M, capital M, times mu of the Proca star. Then identifying the mass of each Proca star as half of the final black hole determines the mass of the ultralight boson. So thus we get a distribution for the mass of the ultralight boson. Thus, if, even just as a proof of concept, one takes seriously the Proca model, we can use GW190521 to infer the mass of the ultralight boson, which in this case is a vector particle. And we've obtained a mass distribution centered around, as I've said before, 8 times 10 to the minus 13 electron volts. Of course, we need more data and more events to really test this possibility. In the most likely case scenario, this is just a proof of concept showing how can there be a degeneracy in real data between two very different models, but also how one can extract physical information potentially about the new fundamental dark matter particle from the data. In this case, the mass of the bosons. Of course, in a much more exciting possibility, a potential confirmation of this bosonic star scenario would be a hint towards the nature of dark matter, or at least part of it. Now, you may be asking, but then, okay, why not the other gravitational wave events? Why?
To ask your conclusions.
Yeah, yes, 2 minutes, please. Why could this event be such a Proca star collision and not the other events detected by LVK? Well, as you may remember, the mass of the ultralight bosonic particle determines the mass of the maximum mass of the corresponding stars. So in this case, this turns out to be about 173 solar masses. All other events correspond to a smaller mass. Since we have observed black hole formation due to the ring down, then these cannot be Proca star collisions. For the Proca star collision to form a black hole, they have to overshoot this limit, which was only observed for GW190521 until the moment when this event was reported. So as a teaser, let me just conclude my talk with this out-of-date stellar graveyard diagram of the gravitational wave events. Well, it's an interesting possibility since most, if not all, the evidence we have for dark matter is really gravitational. To entertain the possibility if the long-sought signal concerning the nature of dark matter could also come from another type of gravitational experiment, and that could be gravitational waves. So with that, I conclude, and I apologize for taking so long. Thank you so much.
Thanks, Carlos, for the nice talk. Okay, we have time for one question, and I see that Robert has posted a couple in the chat. Robert, you would like to speak up?
Yeah, thanks for a nice talk. How would these boson stars form?
Gravitational cooling. So this started to be analyzed by Seidel and Su and back in the 1990s. So if such scalar field would exist with this type of masses, so gravitational collapse would actually make them clump into compact objects, but then you need the dissipation mechanism. Like you have in usual stars, which is typically electromagnetic. But if they are dark matter, then you cannot evoke that. So here it would be the ejection of a high mass and energy, so high energy scalar particles, like kind of fluid ejection. And they've called this mechanism gravitational cooling. So they did some analysis back in the 90s in the scalar case. And we've repeated this for the Proca case some 5 years ago, and it works. That is, if you start with some diluted distribution of the bosonic field, then the evolution can form these stars, that is, can form compact objects.
Thanks.
Thank you.
Masahide, you can pose your question.
Okay, thanks. Hello, nice talk. And yeah, related to the Robert's question in the chat, I'm wondering the stability. And as far as I understand, without gravity, Q-ball, so-called Q-ball is such a correspondence. I mean, the complex scalar field with the UBI symmetries. And in case of the Q-balls, its stability and existence is guaranteed only for the potential flatter than the m square pi squared. But in your case, potential is completely just a mass term. And why, if you take into account gravity, this simple m square pi square potential makes the system stabilized?
Okay, thank you for a question. So not all of these stars are stable. There's a stable branch of solutions. So you see the non-linear interactions that you get in Q-balls by putting your sextic potential, now they are provided by gravity, because gravity, general relativity, is non-linear, right? So you don't, the non-linearities are there from construction. So you can prove in the Q-ball case that with just a mass term, you cannot get any solutions that are stable. You can prove that from virial identity. But actually in gravity, it circumvents that because of the non-triviality of the background. So the simple answer I can give you is, in the Q-ball, we know we need self-interactions. It's not any kind of self-interaction. So if it's just a quartic self-interaction, it doesn't work. You need to go at least to sextic. Now, gravity, the coupling to Einstein general relativity, does provide to you some self-interactions that allow these to be, not only to exist as solutions, but some of them to be stable up to the maximal mass. And then the stability can be shown by doing perturbation theory, and it has been done by several authors in the last 3-4 decades, but also by this nonlinear evolution. So you can actually, even just do fairly non-trivial deformations of the initial star, and it still kind of comes back to something near the original shape. So it's, I would say, very convincing that there is a stable branch of solutions. For the spherical stars, because when you go to the spinning stars, this was an unknown territory until fairly recently. And there was this surprise, which is that in the scalar case, even the simplest model, if you just take the mass term, they are not stable. There is this non-axisymmetric instability that pops out, which is common also to toroidal neutron stars. Whereas in the vector case, then you have that they are dynamically robust. One cannot prove, by the way, via numerical evolutions, stability. It's not a mathematical demonstration. One can only show that they are sufficiently long-lived. And it would be actually very nice, and that's something that is missing, to make a proper perturbation analysis or some other mathematical argument. What one can assess is that the instability that can be seen in the scalar case cannot be seen in the vector case, which we associate tentatively to this toroidal versus spheroidal morphology. But if you actually put in self-interactions, now with gravity, then some groups, ourselves and also a group at PI, has shown that indeed this mitigates the instability and can even tentatively quench it completely. Again, it's numerical evolutions, but the way the timescales are evolving with the parameters, and as you add self-interactions, it seems to be convincing that self-interactions can actually quench completely this non-axisymmetric instability. So,
okay. Yeah, but in my intuition, you see, gravity is always attractive. And if we have an inhomogeneity, it's easily develops. So in comparison with the case without gravity, still I'm wondering that why this kind of the, how to say, soliton-like object, which has a more gradient energy, can be stabilized against the gravity in comparison with the case without gravity. It's a bit counterintuition for me, but let me think it more. Yeah.
Sure, of course. Okay, thank you.
Yeah, thanks.
Okay, so as I do not see other questions, and we are also a bit over time, let's thank again Carlos.
Thank you so much.
The next speaker, who is Alexander Andrianov.
Yes, I'm here.
Hi, Alexander. Can you start sharing your screen?
Okay.
You should go to, okay, I can see something.
So, you see my slides?
So yes, we see your slides, but they are really zoomed in. So is this supposed to be a slide, or it is just
Sorry.
no, so they are slides. So they you should click on full screen.
Yes.
It should be in the options, so select distance.
Наверное, это там, где просмотр.
Or perhaps can you reduce the zoom the moment it is like...
Now it's okay?
No, no.
Вот здесь полноэкранный режим. Ниже. Вот это, да.
Yes, exactly.
Yeah.
Perfect.
That's it.
Perfect. So next speaker is Alexander Andrianov, and he will talk about the black hole formation due to the collapse of the dust shell. So please, Alexander, you can start whenever you want.
Okay, thank you very much, organizers, for invitation me and to give an opportunity to present our recent results in our collaboration. Collaboration is me, Artyom Starodubtsev, and Yasser El-Mahalavi from Egypt. So I will explain how to quantize actually in 2+1 dimension when the space is filled with cylindrically symmetric dust shell and possibly cosmological constant which generates DTZ black hole. So shortly, after Gerald Toft, we know that general relativity in 2+1 dimension coupled to point particles is exactly solvable at the classical and quantum level in principle. But we extend our consideration to the cylinder of dust shell. I will show the canonical analysis of a model in which gravity is coupled to this cylindrically symmetric dust shell. we find canonical variables, providing the global chart for the reduced phase space of the model. Global, which means on the Penrose diagram, it covers all Penrose diagram. For quantization, it is very important. Then we find the canonical. So we perform quantization in the vicinity of horizon, and then present the quantization in the whole space inside of black hole. So first, preliminary remark on how this problem was solved before. So predecessor Victor Berezin, in these years, he did actually some important work in the ADM approach, phase space for transversal actually not transversal, one is fixed by gauge condition and for two components, and this is a Hamiltonian constraint. We see principally we can start from our space-time, or our chosen space-time, which is out of black hole, and look to the interior of black hole. The whole diagram contains also white hole and parallel world and interior white hole. One can see that to proceed, to penetrate to the whole diagram from this Hamiltonian constraint, one has to introduce complex time, proceed to the complex time. So Wheeler-DeWitt equation, if you try to find a spectrum, Wheeler-DeWitt equation becomes the following. For the wave function, we quantize where the parameter of zeta is a fixed number, but we have to quantize in the complex plane. It was achieved by Victor Berezin. One of us proposed, Artyom Starodubtsov proposed another parameterization of entire phase space in totally real variables, and this is important. Now, few words about Bagnados-Teitelbaum-Zanelli solution for the black hole, which appears when we introduce a negative cosmological constant. This is a metric for this black hole, classical, yes. The BTG black hole is locally isometric to anti-de Sitter space ADS2. It is important to know for the further development. Now, action principle. For this connection, we introduce connection for SU22, and with the help of triad, and Lawrencium connection is in fact as usual in geometrical notations. And total action consists of our model under consideration from a sort of Chern-Simons section in terms of this connection, and shell action, so one dimension less, which is spherically, cylindrically symmetric. Look, what we do, we represent shell as an n particle and consider a particle configuration for each particle, sort of holonomy, this picture, and then increase the number of particle and prepare, finally prepare the circle, cylinder. We apply the results of our predecessors, Toft, Matchul, Welling to each particle, solve the constraint, plug the solution back to the action, and a symplectic form for the disk collapses to its boundary. For cylindrically symmetric arrangement, we find the total sum of the symplectic forms in such a form where the holonomy, full holonomy around the full shell is composed from holonomies around each particle. You see, we go to the origin, then to the particle, from the origin, rotate and go back. So in the neighborhood of the horizon, this element is very small, and symplectic form can be simplified further on. The holonomy plays a role of momentum of the shell. This guy is coordinate, then holonomy is momentum, is a symplectic form. It has two independent components, special rotation and boost in radial direction. So if you go back, so I'm talking about this limit. But of course, it has a symmetry, and so we expect the constraint, Hamiltonian constraint. This kind of holonomy provides a global chart for the entire momentum space. This is momentum space. A global chart, and there are several sections which are in correspondence to the Penrose diagram. This is roughly our universe. It is horizon, anti-horizon, white hole, black hole, and parallel universe. The coordinates, we introduce coordinates for three-dimensional flat space in which ADS2 is embedded. It is written here in this part. So let's derive constraint. We use cylindrical symmetry, then this holonomy is presented by the product of individual holonomies around each point. Then M capital is overall bare mass of the shell. I is discrete angular variable, and finally, these transport coefficients are written as according to the geometry in such a form. And to realize a condition that trace of holonomy is this cosine, M is ADM mass, we get Israel equation. Israel equation, pay attention to plus minus. And we can introduce Euler angles, rotation and boost. In terms of these variables, we have two independent equations on the components of U. This and this. No imaginary variables. Q is a short notation for such a combination. And for small q, much less than 1, so these guys are pretty small, it is the limit of this value for ADMS. We find a single Hamiltonian constraint. Now we can quantize. We introduce now wave function as parameterized by these two variables. So rotation, boost and rotation. And the scalar product is defined with the weight, with this weight naturally. Time is canonically conjugated. So I remind that these variables are in the momentum space. So time is canonically conjugated to the variable rho, is a derivative. And the eigenstates, well, once function our variables rho are included in the chart periodically, that all constraints are periodical in a row. And then we expect after this transformation to the coordinate space, we find a discrete time. So it is automatically discrete time. Time operator is T, but it is discrete. Okay, perimeter radius of the shell R and coordinates of the shell in respect to horizon. Now it is around horizon, are related in the following way. So this is a perimetrical radius, 2 pi r is the length of perimeter. And here, in fact, it is this is a Casimir operator. L squared is a constant related to cosmological constant, or better to say to gravitational coupling. So the invariant distance to the horizon, this one, is represented as Beltrami Laplace operator in the momentum space, where this is a Beltrami operator. For positive, outside of horizon for positive x squared distances, the spectrum is continuous, but separated from zero. So for zero values of spectral value, we have still the radius to the horizon. Then to the shell. For negative value time-like inside the horizon, the spectrum is discrete and includes zero. Here, sorry for some misnotations. This L is constant, this L is discrete value. Eigenfunctions for the discrete spectrum are obtained with the help of ladder operators. This ladder of operators help to increase and decrease, raise and raise the indices, and the wave functions are presented here. So for continuous spectrum, the wave solutions has an asymptotic over plane vane. This is outside of horizon, and linear combination of solution is chosen from the condition that there is a balance between incoming and outgoing waves. This is normalization. Now, quantum version of the Hamiltonian constraint is a finite difference equation. I remind that T is discrete. Hamiltonian is represented in terms of all these constants, this distance, and rotation angle. This is a equivalent of Klein-Gordon-like equation for discrete time. The solution is evolution. Actual solution in terms of evolution operator is presented here, where evolution operator is related, is described in terms of Hamiltonian manifestly. Now, dynamics, horizon. We can penetrate after quantization. We understand that we can penetrate, there is a solution through horizons. Classical solution is up. We can go from universe to the interior of a black hole, this one. But we can go back from inside. It is not yet black hole, it is interior of shell, but it looks like black hole. In fact, it has horizon, and there is a penetration outside, but here it is decreasing much slower, but here the decreasing is exponential, damp away. So, intermediate conclusion. We will show what to do with the quantum description of BTZ black hole due to collapse of a dust shell in near horizon region. We actually showed already. Sorry, I have to say that I have inserted already. No, I didn't insert. This description around horizon is valid also for BTZ black hole, but only around horizon of shell. Shell radius has a continuum spectrum, outside of the horizon and discrete inside. But time is discrete always. We evaluate transition amplitude between different regions of the Penrose diagram and find a possibility of quantum tunneling out of the black hole. Why I say it is applicable to BTZ black hole, because around the shell horizon, in fact, the commutative from the horizon, including central singularity point, momentum non-commutativity cannot be momentum coordinate in sense momentum. Momentum non-commutativity cannot be neglected. And now I proceed to the second part. Which exists in printed version only as did not yet appear. Entire quantization of the BTZ black hole, so which appears when cosmological constant is present, negative present. It requires, it cannot be commutative, neither in coordinate nor in momentum space, and so we have to use full-fledged quantum group technique. So this is what we have. We start from coordinates. We build the deformation of algebra of observables with the IQ depending on where we are, outside of black hole or inside, with the deformation parameter either real or square root, not square root, roots of unity. Quantum double, we need to describe this system. D quantum double is a unity of a quantum universal developing algebra, this one, and its dual quantized algebra of function on a group, this one, with commutation relations between the two. I mean, roughly momentum and space. Coordinate space equivalent is this guy. Quantum universal developing algebra in coordinate space, we is the algebra of deformed translations in ADS3 space. These are generators of this in fact enveloping algebra. Algebra is given by this, you see, it is deformed algebra as respect to SL2. Here we have the closure of this algebra, also deformed, nonlinear. Casimir, instead of x plus x minus, we have deformed, of course, deformed operator, and age dependence also deformed. Momentum space, another part of the double, conjugated part. is SLQ holonomy around shell. Around the shell is described by 2x2 matrices, as in classical case, but it is non-commutative matrix. It is non-commutative algebra. This is equivalent of the determinant of these matrices, deformed. And this is a full algebra. You see, some generators commute, some are deformed. And the most complicated is a commutator between A and D, which is related to BC. So this is, now there is a closure of this double with the between U and functor. It is given by the following relations. Is a relation between U and fun. So now we build the world line of this, let be a non-commutative space. The algebra A22 Lawrence generators are given by two operators, and translation generators are given by also two operators. P, then depending on total energy, cell collapses either to point particle with a trajectory around P0 or to BTC black hole around P1. So time-like singularity in the first case is described by this section. It is Chern-Simon section shown at the beginning, and this is roughly this is a connection which describes the trajectory of point particle. Double is given, described for real Q. It's deformation with real Q. And mostly Q is real, A is complex conjugated to D, B deformed to C, H, Hamiltonian, is conjugated. Hermitian, in fact, conjugated, but Hermitian. Coordinates x plus minus are anti-Hermitian. Black hole. Then we have space-like singularity, and the trajectory of a point is described by different projection on the space-like translation. And now quantum double is given with the Q root of unity. Is a different type of representation. Here, the algebra, it is real. B. Hamiltonian is anti-Hermitian. This is cross-conjugated. This is anti-Hermitian conjugated over the same generators. So from cross-commutation relation, we find the following. You see, this guy is from roughly from coordinate space, which is universal enveloping algebra, and this guy is from momentum space. Yes, this is, it describes their relation, and two more by replacing A by C, B by D. When Q is going to 1, which happens by definition when generator of this, when cosmological constant disappears, then a correspondence with the Hamiltonian is given by time operator, and so this is what we expect, that time operator will be also discrete. With this notation, we find algebra as usual for non-deformed case. What is important? And if Q goes to 1, A plus D plus this imaginary part modulus is first of all bounded from below this 1. So normalizable states are given by this generator. Generator is by these generators, this and this. And it is good because these variables, A, D, some of them may cross 0, but this combination is bounded from below, so it can be put down in the denominator. So we start from LL, which does not contain raising operators, and then we build from the roughly ground state, we build the whole tower of eigenstates. Then we find that for discrete, sorry, for roots of unity, this operator just be interchanged by these degrees. This operator for the root of unity is 1, and these raising operators are vanishing. So the representation will be of normalizable states will be finite number of states. So coordinate operators acting on momentum variables. Eigenstates of this operator, which is exponentiation of Hamiltonian, and eigenstate, so one can look, sorry, this definition, yes, H tilde, and find the spectrum of this modified H tilde energy spectrum. And of course, as I mentioned, if Q is imaginary, oh, sorry, Q, yes, it is root of unity. Q is not imaginary, it is a root of unity, then the spectrum is finite. For this case, Casimir, not only for this case, for both cases, Casimir is given by this formula, and it is outside of the black hole is real, and inside is actually is also real, but has a different, because it finally describes the radius, and but it has a different spectrum as respect to this case. I remind here what is n. It is the discrete value given by the product of neuron coupling constant and square root of cosmological constant normalized with h bar. Integrals, when we check normalization and calculate all averages, integrals are given by generated by these formulas, by monomials. So near R equal 0 singularity. In fact, we reach R equals 0 singularity only for the specific choice. In general, is for specific choice of constant n. Let's hope that this constant n is integer, then we can reach it. Look, Hamiltonian near this singularity has the following form. And this evolution of the operator is given by this Hamiltonian. We start from R equals 0 and calculate n to one step down and several steps down. The result is like this. These discrete points, and evidently in the origin, if any, it is finite. After quantization of BTZ black hole in the presence of shell, cylindrical shell, singularity is finite. So, conclusion, short. The Hilbert space of the shell inside the black hole is finite dimensional. The spectrum of the shell radius is discrete and bounded. Transition amplitudes between different shell radii, including R equals 0 singularity, are everywhere finite. This is conclusion both for shell and shell plus negative coupling constant, so for black hole. So I finished.
Thanks, Alexander, for the nice talk. We have time for maybe one question, if there is any. So I can ask one about your intermediate conclusions. You mentioned that you have the possibility in your approach to quantum tunneling out of the black hole, and I was wondering if this would have any implication for the black hole information paradox.
First of all, in the Penrose diagram, you have seen 4 regions. You have white hole, black hole, universe, parallel universe. Penetration can be around. All boundaries are penetrable. This is what we can show for such a model. So, well, penetration means that at quantum level, information penetrates also. So it is not like classical black hole where you can may enter, but nothing but the thermodynamical effects, nothing can go out. Yes.
Okay.
This is what it is exponentially decreasing, but we did not do anything seriously.
Okay, thank you. As I do not see other further questions, so let's thank again Alexander.
Okay.
And see you in a couple of hours.